Hey everyone, we're back for another discussion. This time it's going to be on blood. I know that in a prior video I told you we're going to be talking about pathologies of the vascular system, but first we need to get our heads wrapped around the idea of exactly what's flowing through the vascular system. That is, before we talk about the way all those tubes and hoses can go wrong, we have to understand fully what's going through those tubes and hoses. And there's basically four components to blood. One, plasma. Number two, platelets. Three, red blood cells. And four, white blood cells. Plasma is somewhere between 40 and 50% of the composition of your blood. For men, it's a little bit more than for women. The white blood cells and some other things, sometimes actually when we separate it out, as the image you can see, when we put it in a centrifuge and separate it out and actually sort of pull the red blood cells out, we talk about a buffy coat because the color's kind of buff, and that is the white blood cells. And as you can see, that's a pretty small percentage of all the stuff in your blood. And then the rest is plasma, and plasma is largely water. But let's talk a little bit more specifically about what plasma is. First, yes, it's largely water, or if you'd like, if you were to pull out some blood and separate it, it'd be the yellowish liquid portion of the blood that's kind of carrying everything. Now, as I said, that's about 92% water, and I'll talk about that in a minute. But in addition to that, it is also some proteins, some nutrients, some minerals, some electrolytes, hormones, which we haven't talked about, but basically catalysts that signal your body to do certain things, those are in there as well. Basically, anything that's going to circulate around your body is probably going to circulate through your bloodstream. But the biggest one is proteins. Now, at this point, you might have as a question, why are there proteins in my blood? And you might think, is it because these proteins are making me strong and building big muscle? Yeah, sure. Proteins do that, but that's not why they're in your blood. The proteins in your blood are interesting. They're actually principally albumin, and then there's also some globulins. Now, I don't care too much if you remember those terms, but albumin is like egg white. And globulins are a collection of different sorts of molecules of proteins that basically glob things together. Why are they in your blood? A lot of reasons, but one of the principal reasons is as carriers. You see, there's other things that your body needs to have circulated that aren't going to mix well in blood. Things that are lipid-based, that is to say, things that are oils. So, for example, some of the hormones, some of those signaling molecules that I talked about, those are actually fat-based. Then there's also some fat-soluble vitamins. And then there's also electrolytes that may not mix well with blood. For example, iron doesn't float and get carried well with blood. So these proteins actually bind to and carry these things around in your bloodstream. This should make sense to you because if you take oil and water, you know they don't mix. Heck, it's actually an expression. Oil and water don't mix, right? Most of your blood is water. Put oil in there, even if it's in the space in the context of adrenaline, which is oil-based, it's not going to mix well. And the last thing you want is like globs of oil traveling through your bloodstream. You want it fully suspended and carried around in your bloodstream. These proteins will connect to these lipids and carry them around throughout your bloodstream. If you've had some chemistry, you'll know that the reason for that is that proteins are polarized and water molecules are polarized, so they can interact with each other, and therefore proteins can be carried easily in the water. If that part really confused you and you have no idea what I'm talking about, fine. You don't need it for this class, just forget I ever said it. But for those of you who had some chemistry, that might help this make sense a little bit. Okay, so we've got about 7-ish% protein, and those proteins are principally there to carry around things that otherwise wouldn't dissolve in the water. The other thing that these proteins do is they create an osmotic gradient. Now here I am tempted to say, and you don't need to understand that very well either, but you kind of do. So I want to explain osmosis to you in really simple terms. And here's how I'd like you to think about it. Imagine we have, I don't know, an aquarium. Does this look like an aquarium? Filled with water. So far, so good? And let's imagine that I put a membrane in the middle of that aquarium. Some just like sheet of something that separates the two parts of the aquarium. And now, let's say that I put a bunch of salt on this side of the aquarium. And let's say that the salt can't get through that membrane. So I don't know if you can see that, but I'm just making a bunch of dots. That's all the salt I dropped in the water on the left side of the aquarium. Okay. If I leave this alone and come back in a few hours, do you know what happened? It's super interesting, actually. What would happen is the water would want to get over to the salt side. This is what we mean by osmotic pressure. Basically, water wants to stabilize the gradient. If we have more of a particulate in one side than another side, the water wants to get drawn to that side with more particulates and even it out. So if one side had 3% water and the other side had, 3% salt and the other side had 5% salt, water would want to go to the 5% salt side to even it out. We call that an osmotic gradient. Now, in this case, if I come back later, what I'll find is that the water on this side goes up and the water on this side goes down. Basically, the water will move through the membrane to try to equalize the two sides. That's osmosis. If in really simple terms that makes sense, that's probably good enough for this class. But why do I want you to know that? Because that's one of the main purposes that, or the benefits of these proteins, is they create that osmotic gradient. In other words, when you have a lot of proteins in, like the salt, they draw water in. You see, your vessels actually allow water to go in and out of them. This is how you get things like inflammation or swelling. When a part of your body swells up, that's actually water coming out of your bloodstream and into the surrounding tissue. And that can happen times when you don't want it to happen. The protein and salts and electrolytes and other things in your blood keep that from happening by pulling some of that water in. And sometimes in medicine, we will adjust that osmotic gradient. That is, create more particulates in your blood in order to draw more water into your bloodstream and less water in the surrounding tissue. Because that's the thing that people usually don't understand. They think of blood as like this separate kind of thing. It's not. It's mostly water, and it's coming in and out of your body. It's not just contained in these vessels. In and out of your tissue. It's not just contained in these vessels. It's constantly seeping out. We call that filtration, and being drawn back in at times. So that's why when you have swelling, it's actually water coming out of your vessels and into surrounding tissue. There might be other examples of this too. So for example, let's say you get really dehydrated. Dehydration is the loss of water. Now, you might not think about it in this way, but that means the loss of blood. And so if you get severely dehydrated, you could go to the hospital and they could say, yep, you're hypovolemic. Hypo means low. Volemic is volume. In other words, you've got a low volume of blood. And that means your heart's going to have trouble pumping blood around and creating adequate circulation of blood to all your tissue. It also means that the blood you have left is going to be thicker, because the proportion of red blood cells and electrolytes and salt and proteins gets higher if you draw some of the water out. So then you get thicker blood that's going to be harder to pump, and you've got less blood there. No wonder it's a bad idea to get dehydrated. Now, it's just not, say, dehydration from being, outside in the heat. It could be dehydration from, say, diarrhea. So if somebody has some kind of an intestinal infection and has severe diarrhea, this is potentially a life-threatening issue. People literally around the world die of diarrhea, and they do so because they get dehydrated. And as a result of that dehydration, organs stop functioning, blood stops circulating properly, it has trouble providing oxygen and other needed nutrients to parts of your body. Remember, we talked about that homeostasis before. Everything we want to keep stable, your body doesn't tolerate big fluctuations. Well, guess what? A significant loss of blood volume, hypovolemia, is a big fluctuation, and that's problematic. So your plasma is actually an important part of your blood. Another part of your blood is platelets. Platelets are kind of interesting. What they are is actually bits and pieces of cells that are formed in your bone marrow. So there's these cells formed in your bone marrow. They break apart before they leave the bone marrow, and they create what are called thrombocytes. That's just another word for platelets. Thrombo, whenever you see the thrombo, you can think that it has to do something with clotting, right? Well, that's not surprising here, because that's one of the principal roles of platelets, is to make it easier for your blood to clot. So these platelets are called platelets because initially when they go in your bloodstream, they look like little plates. Get it? Platelet, little plate? Okay, fine. They're small, they're colorless. You would see them in your blood and not think much of them, but their job is to stop you from losing your blood and dying. That is, when you get a little cut or a big cut, they're the things that form that initial jam that will allow other parts of your blood to create a clot and stop you from losing a lot of your blood. So they're born in your bone marrow. They're shaped like little plates. You get a cut, and these platelets that are floating around, these little bits and pieces of cell, jam up in that opening. We'll talk about this process later, but they jam up in that opening and they create sort of a block. And then other different kinds of particles in your blood create a full-on clot and stop the bleeding. What's interesting about these platelets is the way they change. Here's an image for you. Now you can see from that image that that little thing there on the right is the platelet. The thing on the left is a red blood cell, and the thing on the upper right is a type of white blood cell. But what I'm interested in is the platelet, the thing that looks like, I don't know, a diseased octopus. When platelets get activated, when you have a bleed and they jam up, they grow these tentacles and they get super sticky and they connect and combine with each other. That's the amazing thing about platelets, is they flow through your bloodstream, not creating any problems at all, totally fine, and then you get a cut, they immediately go to that opening, they get super sticky, they jam up and create kind of a log jam that allows other parts of your blood to then clot up. It's very cool. Now, because they're only bits and pieces of cells, they don't last very long. So we're constantly replacing these platelets. They last about 10 days, and after that, some of your defensive cells go in there and eat them up, something we call phagocytes, which are specialized defense cells that kind of go and eat up debris and things like that. And in fact, about a third of them aren't even floating through your bloodstream. They're in your spleen. We'll talk about the spleen later, but they're basically in this organ sitting there so that if you get a bleed, if you get an injury and you start bleeding, they all get deployed. And because they're circulating throughout your bloodstream, they go to where the bleed is and they jam it up. That's their principal goal. Okay, red blood cells we've already talked about, so this should sound pretty familiar, but we didn't talk about it fully, so I want to give you a little bit more information. Red blood cells also form in the bone marrow. Remember, they carry millions of molecules of heme that allow you to carry iron, that allows you to carry oxygen to all your organs and tissue. So this is an amazing process. I've already convinced you of that, I think. But in order to carry all that heme, in order to be able to carry as much oxygen as possible, they can't be burdened with other kinds of cell machinery. So they are born in your bone marrow. Before they leave the bone marrow, they actually spit out their nucleus so that they are without a nucleus when they actually get in your bloodstream. The reason for that is that it gives them more capacity to carry more heme, and that is, after all, their goal. As a result of that, they're not going to have a real ability to fix themselves. In fact, they're going to spit out, after they mature, after just a few days in your bloodstream, all the rest of the machinery of a cell. So those first few days in your bloodstream, we call those reticulocytes. What these are immature red blood cells. And it's kind of useful to know about this because physicians use this all the time to see how you're doing and potentially get a diagnosis. In other words, I'm going to take a sample of your blood, and one of the things I'd like to see is how many very young red blood cells do you have in your blood? And the reason I'd like to know this is because if it's a lot, if it's more than normal, there might be a reason for that. Are your red blood cells falling apart too soon, and so your body's making a lot more red blood cells? Are your red blood cells not working properly at carrying oxygen, and so your body is making a lot more red blood cells? If you have certain diseases, from leukemia to other types of cancer to other issues we'll talk about related to blood pathologies, your body is going to respond by trying to make a lot more red blood cells. So if I see a higher proportion of red blood cells, I'm suspicious, and I want to make sense of that. Blood cells typically last only about 120 days. So they normally break up fairly quickly. 120 days is not a long time. Why do they break up so quickly? Because they don't have the machinery inside them to allow themselves to repair themselves. And they've made that sacrifice so they can carry as much oxygen as possible. But this also means something interesting, which is your body needs to have a mechanism for removing all that debris. When these red blood cells break apart, they're going to be bits and pieces of broken red blood cells everywhere. Bull in a china shop kind of thing. And guess what? We have organs. The spleen is one of them, and others, whose job is to pull out and deal with the bits and pieces of red blood cells that are left. Here's an image that you can see. And can you see in this image of red blood cells, the ones that have like the blue, darker blue marks in them? That's interesting. Those are the reticulocytes. So if we were doing a blood test, we would look, and we have ways, computerized ways, of counting up what proportion of reticulocytes there are and making sure that that's within a normal range. Once those cells that are there with the little darker colors in them, the reticulocytes, once they mature in just a few days, they're going to spit all that out because they want to maximize their capacity to carry oxygen. Let me talk here a little bit about how even what we've talked about before should make sense of something that might not have made sense before by talking about erythropoietin, or EPO. Okay, your kidney, to take a step back and explain this, your kidney has a lot of blood flowing through it. I mean a lot of blood flowing through it. Like in the space of a day, about 50 gallons of blood flows through your kidney. At this point, you're saying to yourself, Hasse, I don't have 50 gallons of blood. And you're right. Well, the blood circulates through many times. So the blood is circulating constantly through your kidney, and your kidney's job is to clean it out. In fact, one of the things it's going to clean out is some bits and pieces left over from red blood cells that have fallen apart. Okay, fine. But what this means is your kidney is also an ideal organ for seeing how well your blood can carry oxygen. So your kidney has mechanisms in it, sensors in it, that can sense the amount of oxygen in your blood. And when it gets low, it's going to take a signaling protein, just like what I described before. If you've had chemistry, we could call it an organic catalyst, but basically a special molecule that's erythropoietin. And it's going to send that messenger to the bone marrow saying, make more red blood cells. Okay, so far this is cool and should make sense. The kidney is checking your blood constantly to see if it's carrying enough oxygen. If your blood is not carrying enough oxygen, the kidney sends a signal to the bone marrow saying, make more red blood cells, the blood is not carrying enough oxygen. And the signal it sends is EPO, erythropoietin. Why am I bringing this up now? Because I can't help myself from explaining sometimes how this stuff is so cool and relates to all kinds of aspects you hadn't considered before. Because you know what else EPO is used for? It's used as an illicit stimulant in endurance sports. This is why Lance Armstrong and others got in trouble. They were doing injections of synthetic EPO, what's called EPO. And what does that do? It's a signaling compound that told their bone marrow to make more red blood cells. Can you imagine why if you're, say, doing a month-long bike race, we are covering 100 to 300 miles a day, it might be helpful to have more red blood cells? Heck yeah! Now, does everybody have the same amount of blood cells? No. In fact, if you live at altitude, so if you're a professional cyclist and you train at a high altitude, you'll have more red blood cells. And the reason is because your body will adapt. There's less oxygen in the air at high altitude, so your body will make more red blood cells to be able to carry all the oxygen your tissue and organs need. So Lance Armstrong said, look, this isn't really cheating because I could just as easily get this advantage by training in Colorado. Okay, fine, Lance, but you didn't. You did it with a synthetic version of a signaling molecule that is artificially telling your bone marrow to make more red blood cells. And as a result of that, your tissue, your muscle tissue, is better oxygenated for those, like whatever they are, 10-hour days on a bike traveling at 25 miles an hour. So you can see why that's an advantage. Is it also a disadvantage? Is there a risk? Yeah, there's a few risks. But one of the big risks is what we talked about before. If I add more red blood cells, what happens to the viscosity, the thickness of my blood? It gets thicker, right? Just like we talked about before, if I reduce the amount of water in my blood, it gets thicker because the solid stuff is still there. I just have less water mixed with it. If I instead add more solid stuff by, let's say, adding more red blood cells, also gets thicker. So is this a problem? Well, it would make an athlete's heart pump a lot harder because now it's got to circulate a much thicker blood. It's possibly going to compromise blood flow to certain organs or certain tissues. So yeah, there's a risk. There's an advantage, but there's also a risk. And this is one of the many reasons that professional sports don't allow athletes to use this. So you can see now where EPO kind of makes a lot of sense in this context. The other thing that's going to be removed from cells, let me get rid of this, is bilirubin. Bilirubin, I think it's a German word. I don't really know where it comes from. It's a weird word. But what it's referring to is some of the bits and pieces of red blood cells that have fallen apart. So this is basically the non-iron portion of the heme. So remember what the heme is, the hemoglobin, right? And the iron is in the hemoglobin, and that's what's carrying oxygen. Okay, when it falls apart, the iron separates out. We reuse that iron. And the bits and pieces of the hemoglobin, that's the bilirubin. Okay, that bilirubin is kind of a yellow, brown, mustard yellow kind of color. Here's an interesting thing. When the liver is stressed and starts to fail at filtering blood, remember that's one of the things the liver is doing, is pulling out these bits and pieces, then the bilirubin will build up. And if the bilirubin builds up, it's going to start building up in your tissue. Because remember what we said before, the blood isn't just contained in your vessels. It is constantly being exchanged back and forth with the surrounding tissue. So if we've got a lot of bilirubin, excess bits and pieces of hemoglobin, broken up red blood cells in your blood, they're going to make their way into the tissue. And you're going to see that because that's going to make its way into the skin. That's after all, what your skin is. That's tissue, right? And we call that jaundice or yellow skin. Here's an image for you. Can you see how this person has sort of yellow in the eyes especially, but yellow in the skin too? It's not just in the eyes, just easier to see in the eyes because it's normally a white background and now you got yellow in it. But depending on somebody's complexion, that yellow can be pretty significant. That is called jaundice, and that's a pretty clear sign that the liver is having some stress and some issues to it because the liver's job is to clean that out, and it's not cleaning it out. In severe cases, this gets pretty weird. Like you could wake up in the morning with yellow stained sheets. You could have yellow stained clothes because that yellow, that bilirubin is coming out in your sweat. It's working its way out through your pores and it will literally stain your sheets yellow. This is also one of the reasons, or how should I say this? This is going to provide an answer to an age-old question that you've always asked yourself. Why is my poop brown? One of the reasons your poop is brown is because there's bilirubin and other particles in it that have a brown color. And so one of the things you're doing when you're pooping, you're getting rid of bacteria, you're getting rid of fiber, you're getting rid of all kinds of things that you couldn't digest, whatever, the corn bits and pieces, you know the drill, all that stuff's coming out with your poop. But the other thing that's coming out with your poop is bits and pieces of red blood cells. Those red blood cells are constantly, there's a lot of them, and they're constantly regenerating themselves. And as they do, bits and pieces need to go somewhere, and some of them are going to end up in your poop. Then we've got white blood cells. Now, I don't really want to talk about white blood cells right now because we're going to have a whole discussion of the different kinds of white blood cells. But here's an image for you that at least shows there are a lot of different types of white blood cells, right? They all look pretty cool. I mean, as you look at these, like, okay, I'm of a certain age where I look at these and I remember like posters under black lights in the 1970s, right? And you smoke a little weed and suddenly those little globs start moving around all directions and it's pretty freaking awesome. Maybe that's not what's coming to mind for you. But either way, they look pretty psychedelic and pretty crazy. There are a lot of different kinds of white blood cells. They're basically defensive cells. So the thing to know about white blood cells right now is they are the cells whose job is to protect you from infections by tiny little organisms, tiny little worms, bacteria, viruses, things like that. There's one more thing I want to talk about before we wrap up this session on blood, because already you know the main components of blood, so that's cool. But I want to talk about blood typing as well, because you hear this all the time and you probably even know your blood type, but I wonder if you know what blood type means. So here's the thing. We didn't. No one did really before 1900. So before 1900, people would get transfusions and a lot of times they'd die. And the doctors of the time were kind of like, I don't get it. We're putting blood in the dude and he's dying. And at that time, it just seemed like blood was blood was blood. So why is this a problem? And then what happened is just a little after 1900, we recognized that blood has different groups to it. And those groups have different key characteristics, and they aren't interchangeable. What we identified at that point is what can be called antigens. Antigen is going to be an important word for us. You have antigens. I have antigens. All God's children got antigens. What are antigens? Antigens are proteins on the cells that allow your defense system to identify whether something belongs to you or not. In medical terms, we often say whether it's self or non-self. So for those defensive cells that are floating around, they're checking things out. They're checking passports, right? They're going through the bloodstream and they're looking at this little bit and saying, is this one of us? Is that one of us? And they're doing this to red blood cells. They're checking out, is this one of our red blood cells? Is that one of our red blood cells? And what they're checking is the antigens. So on red blood cells, well, one way to think of it is this. Here would be a red blood cell, right? And on the outside of that red blood cell, I don't know, there's little things sticking out with a shape to them. Now, I'm not getting the scale right because the proteins are a lot smaller and there's a heck of a lot more of them. But otherwise, this ain't so bad. Like I told you before, I'm not a good artist, but this is pretty right. Like it's a red blood cell with a bunch of things sticking around the outside that have a certain shape to them. And what will happen is our antibodies, which we'll talk about later, but a form of white blood cells, will come up to them and they will see if there's a fit. So they'll have something that kind of fits the outside of this and they'll put it up there and they'll say, yep, that's a fit, you're good to go. Yep, that's a fit, you're good to go. Yeah, that's a fit, you're good to go. And then they'll fit one and they'll go, no, you don't fit. And they will mark that one for destruction. And then other parts of your defense system are going to attack that one. Well, with red blood cells, we have two different possibilities. This is one, and we'll call this A. Doesn't look like that, but whatever. And all the way around, it's going to have these proteins. And then we could have another, and we'll call that one B. And I don't know, the proteins will look different. And again, there's tons of them. They're smaller than these, but they're just little markers. And they go all the way around. So I've only drawn them halfway around because I didn't feel like spending my time doing it. But now that you guys are yelling at me for not doing this right, I'll do it. Okay, you get the idea. They go all the way around, right? So your blood, any human's blood, can either have the A antigens or the B antigens. Or I could imagine a red blood cell that has some A antigens and some B antigens. And that would be AB. So far, not too complicated, right? Is there another possibility? Yeah, there's one more possibility. I could have blood, like my blood happens to be, that has none. It doesn't have A's or B's, which makes it easier to draw. And we'll call that O. We call this the ABO system. No antigens, B antigens, A antigens, AB antigens. So far, I think you're getting the gist. These are the blood types. If you know your blood type, so far, you're one of these, right? O tends to be fairly popular, but all these exist in reasonably large numbers. Now, because these are antigens and because we have defensive systems, we develop antibodies, which are defensive cells that fight against the ones that aren't us. In other words, identify non-self and attack it. So, if you have type A blood, you're going to have an antibody that's going to go after type B antigens. And when there's type B antigens, it's going to destroy them. You think you're getting the trick here, right? If you have type B blood, your body's going to take type A antigens and destroy those. If you have AB blood, you're going to have neither. But you can't, because if you had any cells that attacked A or B, you're screwed. It's going to attack your own cells. So if you have AB, you have neither. And if you have type O blood, you can have both, because either one is going to mark as a non-self. In other words, if I got type O blood and then you put A blood in me, my defensive system is going to say that those A cells, those A red blood cells, don't belong to us. We're getting rid of them. That's a shame, because it means we can't have universal transmission of blood from one person to another. But you can see why in evolutionary terms this makes sense, that the body would identify things that don't belong and get rid of them. Because usually, for most of evolutionary history, the things that don't belong are things that hurt us, what are called pathogens. So a pathogen is something that creates a disease. It doesn't belong to us, and it creates a disease. So as I said, tiny little animals, tiny little worms, bacteria, viruses, etc., that's what your body has evolved to fight. So it's looking to see, does this belong to us? And when it finds a virus that says, no, that doesn't belong to us, we're getting rid of it. So here's a graph that's a little bit better version of what I just drew, and you can see kind of the same thing. Unfortunately, or fortunately, this makes transmission of blood or transfusion of blood from one person to another a little more complicated. And you can see there that certain blood is going to allow you to be a universal donor. So for example, if you have type O blood, you could give it to anyone because your blood doesn't have either antigen. So their defensive system is not going to identify that as a problem. Gets a little more complicated than that. I'll get to the complication in a second. If you, on the other hand, have type AB blood, you can accept blood from anybody. You're a universal recipient because you don't have the antibodies for A or the antibodies for B. You can't afford to because you've got both A and B antigens on your red blood cells. So therefore, you could take A, you could take B. You're not going to get a bad reaction. Does that make sense? So we've got O as a universal donor. We've got AB as a universal recipient. But we're not done yet, because there's one more complication, which is the Rh status, which is sort of weird, but this is where the negative and positive comes in. So you might remember your blood type as being, I don't know, A positive. And you might say, so far this makes sense, Hase, except what's the positive mean? There's another protein called an Rh factor. Rh stands for rhesus monkey because the original research on this was done with rhesus monkeys. So there's your Rh factor. If that helps you remember it, fine. If not, you can just feel bad for the poor monkeys that probably suffered in this experiment. Anyways, what they found is that there's particular proteins that also define compatibility of blood types. Most people, about 85% of people, are Rh positive, so they have that protein. But about 15% of people are Rh negative, so they don't have that protein. And now you get the drift, right? If you don't have the protein, you're going to create an antibody, a defensive cell, that will attack that protein, which means it's just not the A, B, O that we have to think about, but it's also the presence or absence of that protein. We've got to match that up as well, because if you got somebody with Rh positive blood that have that protein, they can receive blood from either somebody who has the protein or somebody who doesn't. But if somebody doesn't have the protein, if somebody's Rh negative and they receive Rh positive blood, well, if they're Rh negative, they've probably developed an antibody to the protein. So now they're going to have a reaction, and that's not going to be good. So we have to match that up or consider that as well. This is why you can now answer that age-old question. On all those medical drama shows, when somebody crashes through the emergency room doors and they're wheeling a patient to an exam room and somebody yells out, "Type in cross-match, stat!" And you've always wondered, you've stayed up late at night wondering what the hell are they talking about? Now you know. The type is figure out if this person is A, B, AB, or O. The cross-match is find out this person's Rh status and then other possible antibodies that might define compatibility of blood. And the stat just means hurry up. So now you can act like a smarty pants next time you watch a medical show with your girlfriend, boyfriend, mother, father, whatever. Before we finish this up, I kind of want to give you one example of how this can get really interesting. And by the way, there's like 1,000 examples of how this can get really interesting. But here's one for you that's sort of cool. In an interesting way, as medicine always is, in an interesting way, if it doesn't happen to you. So here's the thing. Let's say that a woman is pregnant. And let's say that that woman is Rh negative. So she doesn't have that protein. But let's say that her fetus is Rh positive. Now at this point, half of you have just stopped and said, "What do you mean? Doesn't the fetus have the same blood as the mother?" No. The mother and the fetus have separate blood systems. They have connections between the two for sure, but the mother's blood does not define the fetus's blood, right? The fetus develops independently with its own blood type. So it is possible for a mother to be Rh negative and the fetus to be Rh positive. Okay, so if the fetus is Rh positive and the mother's Rh negative, already there's a potential problem, you're thinking, because what happens if that fetus's blood gets into the mother's blood supply? The mother's going to get a response, right? Because the mother's Rh negative, which means she's going to have antibodies to Rh proteins. Well, maybe not. Not initially because she hasn't been exposed to it. So maybe that first baby is going to be okay. And in fact, there's relatively little exchange of blood products between a fetus and a mother. There is some. Back 30, 40 years ago, we thought there was none at all. And then we learned that yes, there's some. So it's possible that this could be a complication early on even in a woman's pregnancy. But it's also possible and perhaps more likely that it won't be. Except at some point, that mother's going to give birth. And then there's going to be a lot of blood, or at least there can be a lot of blood. And then you might get blood exchange. And a little bit of the fetus's blood might end up in the mother. And if that happens, what's the mother going to do? Her defensive systems are going to build antibodies to that antigen. They're going to recognize that baby's Rh protein as a problem, and they're going to build a defensive network to protect themselves. Now the problem comes if this woman gets pregnant again, and she also has a child that's Rh positive. And that could happen after all. If they both have the same father, then there's a chance that they're both going to have the Rh positive protein. Now the problem is the mother's blood has in it a cell, and that cell is going to want to destroy the protein in the fetus's blood. Can you see why this is problematic? The result of that is, as this fetus develops, there's going to be antibodies that are going to potentially get into that baby and destroy red blood cells. And that's going to lead to a lot of bilirubin and other debris related to the breakdown of these red blood cells in the baby that's actually going to have an osmotic effect. Remember we talked about osmosis before? Now you've got a lot of particulates, a lot of bits and pieces of cells in this baby's circulation. What's that going to do? That means fluid, water, is going to be drawn in to the baby's tissue. The bilirubin is going to make its way into the tissue as it did with jaundice. Remember we talked about jaundice, right? So now we got bits and pieces of red blood cell in the baby's tissue, in the baby's bloodstream, and fluid's going to be drawn in. I was tempted to show you a picture of what this looks like, but honestly, if you really want to see it, you can Google it. It ain't pretty. The baby, the infant or the fetus is going to be swollen, it's going to be red, it's going to look alien-like, and it's not going to have a real good chance of having a happy life. What do we do about this? Well, smart physicians, my wife included, she's an OBGYN, are going to identify this early, and what they're going to do is they're going to administer an immunoglobulin. That is to say, they're going to administer an immune cell that's going to grab hold of the Rh proteins and prevent the mother's system from ever seeing them. Remember, the real problem here is that the mother's system has identified these Rh proteins and then builds an antibody against it. That's why it wasn't a problem with the first pregnancy, because the mother hadn't built the antibodies. So the clever doctor is going to put in place, inject into the mother a defensive cell that's going to go through the circulation, grab all of those Rh proteins and lock them down. And the mother's defense system, natural defense system, will never see them, and therefore never develop an immune response, and therefore won't be a problem with the next baby. Brilliant, right? This is the kind of cool stuff that happens in medicine, and this is why it's kind of advantageous to know this stuff. And at some point, if you are going to be a physician or a nurse or any kind of provider, you're going to need to know a lot more about this. But even if you're not, maybe you're going to be the mother or father of that child and going to really want to understand this scenario. Or maybe some point you're going to need a blood transfusion, or your baby's going to need a blood transfusion, or your grandmother's going to need a blood transfusion. God forbid, if that happens, I think you're going to appreciate understanding the intricacies and importance of that type and cross-match stat scenario, right? Okay, that's it for now. With the next video, we're going to get back and we're going to talk about some of the diseases and issues that happen with blood, and that'll be cool too. I always like talking about diseases. Okay, see you soon. There we go. That was longer than I thought. I thought that was going to be 50.